Hi, welcome back. In this video, we are going to learn about the general senses, um, and that's all. So when we're talking about general senses, we can divide them into two big categories, the somatic sensory receptors versus the visceral ones. And in the somatic ones, we have proprioceptors we've already learned about, and we have all those tactile receptors that were in our integument, whether it was the skin or our mucous membranes. We already looked at those. So let's review those real briefly and bring them back to the forefront. It's been quite a while since we learned about them. So when we learned about sensory receptors of the skin, there were 7 of them here, and they all had the typical locations. For instance, the Meissner corpuscles were in the dermal papilla, the Pacinian corpuscles were really deep in the reticular dermis or in the hypodermis, and in the middle of the upper part of the reticular dermis, we would have the Ruffini endings and the Krauss end bulbs. Merkel discs always had to go up to the Merkel cells in the stratum basale, so they were always superficial as well. Free nerve endings could either be in the dermis or the epidermis, and the last one, the root hair plexus, well, that's got to be where the bulb of the hair root is, so that's either going to be pretty low in the reticular dermis or in the hypodermis. So let's go through these one at a time in no particular order. And so this time, we're going to talk about the structure of these various tactile receptors. So they're divided into 2 different categories. The first category are the 3 receptors that don't have any type of capsule surrounding the sensory dendrites. And so the first one are the free nerve endings. So this is just a simple dendrite ending of a sensory neuron, primarily temperature, cold and hot, and some pain stimuli. And so the drawing is showing free nerve endings in the epidermis, whereas the photomicrograph is showing free nerve endings in the papillary dermis. So they can be located either place. The next, 2 came up. The next receptor is the root hair plexus, and the root hair plexus is multiple sensory neurons whose dendrites are going around one single bulb of a hair root, and they form this web surrounding it, and so that's detecting movement of hair. And the third one is the tactile disc or the Merkel disc, and when we look at this one, we've got this neuron whose sensory dendrites, the ends of them have been kind of flattened down, almost like this cup shape, so that they can cup up against a Merkel cell in the stratum basale. And so these are the ones that are activated with the super light touch, like with the feather. So that's it for the 3 unencapsulated. And now we're going to go to encapsulated tactile receptors. So in this case, we either have connective tissue or we have glial cells surrounding the dendrites. So stop and think for a second. What type of glial cell might this be? Press pause and think about this before you continue on. Okay, are you ready to see if you're right? Well, we'll get to it shortly. First, let's start with what's called the Krauss end bulb or the end bulb. And basically it's this round structure where we have a whole bunch of dendrites just forming this big blob there, and they're surrounded by some connective tissue. And these are in the upper half of the dermis, so they are going to detect some type of lightish pressure. The next is everyone's favorite, the lamellated or Pacinian corpuscle. And here we have multiple sensory neurons going into one of these corpuscles. So I'm going to show 2, and then all the little dendritic ends. And then what type of glial cell did you decide? Okay, are we in the central or peripheral nervous system? Peripheral, so there's only 2 glial cells in the peripheral nervous system, and they were the satellite cell and the Schwann cell. And satellite cells are only found in ganglia. So this is not a ganglia. So hopefully you were able through that process of deduction to realize that the glial cells that had to be involved were Schwann cells. Okay? And so the Pacinian corpuscle, the reason why it looks like an onion cut in half is all those layers of the onion are Schwann cells. So this is totally different than an axon where we had one Schwann cell wrapping itself around 50 times and pushing the nucleus to the outside. Look at both of these pictures, both the cartoon drawing with all the little dots. Each one of those dots represents the nucleus of a Schwann cell, and you clearly can see multiple dots if you look at the photomicrograph of the Pacinian corpuscle. And so what we have are a lot, like 50 to 100 Schwann cells that are surrounding these couple of sensory neurons. And these are located very deep in the dermis or in the hypodermis because they have to do with deep pressure or a high frequency vibration. Our third type of encapsulated receptor is called the bulbous corpuscle or the Ruffini corpuscle. This is the one that kind of looks like a UFO flattened thing, okay? And so we have some dendrites going into this, and we are back to surrounding it with connective tissue. So both the end bulb and the bulbous corpuscle have connective tissue, but you notice their shapes are totally different. And so the Ruffini corpuscle is about midway through the dermis, and so it's going to detect a continuous type of deep pressure, as well as when the skin just gets distorted, like when somebody's leaning on you for prolonged periods of time. And the last one's the most superficial one, and this is the tactile or Meissner corpuscle that is located in the dermal papilla. And here we have multiple dendritic endings of sensory neurons that are all entwined around each other. And then once again, we are going to have Schwann cells surrounding it, and then we're going to have connective tissue surrounding the Schwann cells. And this gives us light touch, as we talked about. It also gives us texture and shape when we were talking before, how you could identify shape just by feeling something, or by feeling something, you can kind of tell if it's cold like metal. And the other thing this is really important for, which we didn't have a chance to do in lab, but maybe you will in another lab later on, is 2-point discrimination. All right, so that's it for the tactile receptors, and now we have our two proprio receptors we've already learned about. The first was the muscle spindle, where we had those intrafusal muscle fibers completely wrapped up with the dendrites in a little connective tissue capsule, and this was monitoring the muscle stretch and giving us the normal resting muscle tone, and you could tell when the muscle had contracted or relaxed or not. And the last one was the Golgi tendon organ, which was in the tendon very close to where the muscle is. And so when the muscle contracted, this would stretch and let you know that happened. So that's it for those. And now I just want to take a few minutes to talk about some senses you've probably never heard about, but are super kind of cool, and they don't fall into the special senses category. So the first sense has to do with passage of time. So have you ever noticed as you're getting older that time seems to be passing slower? Like when you were a kid, it's like zoom so fast, and now you talk to your grandparents, it's like, oh my God, okay, like maybe this month, it seems like this month has lasted about 8,000 years, I'll give you that. But if we do, there have been experiments, so not if we do, because they've already been done. If we would take 19 to 24-year-olds, so like juniors, seniors in college and the first 2 years afterwards, and we were to sit you in a room without a clock, and you didn't have watches and you didn't have your cell phones, and we would ask you, okay, now without counting 1001, 1002, 1003, without counting the seconds, can you let us know when you think 3 minutes are up? And when this experiment was done, what it found was almost all the students could do that within about 10 seconds. Really accurate, okay? Now, performing the same experiment on people your grandparents' age, their average time was about 3 minutes and 40 seconds, okay? So your perception of the passage of time is going to change as you age, and you just need to realize it at this point. So like when you're keeping your parents waiting and they say it's 10 minutes and you think it's 1 minute, it's your perception versus their perception. Okay, so be kind. You're going to be that age someday. The second sense is something called synesthesia, and this is where sound gets interpreted as colors. And for somebody who does, who has synesthesia, this is their interpretation of part of a Mozart piece. So some people have this, and other people develop synesthesia when they're under the influence of, how should we say it? Things that you might have at Burning Man, like hallucinogens. And that's part of the reason why sometimes some of your best musicians can be very creative when they're under the influence of those substances, because they can see whatever they're creating as colors, and they can see that the colors are harmonious, which is a much easier to see than the discordant sound, and they can't figure out what it is. But by changing with the sound, then they can see the colors and everything lines up. All right. So do you believe this or not? All right. So I had a student a couple of years ago, and after I talked about this in class, he came up and talked to me, and he was a twin. And he said that ever since he and his twin were very little, his twin always talked about sounds as colors. So every one of their pets, like their dog, always barked in red. Every one of their pets had a color, and every person in the family, their voice had a color. And so, like for instance, when company would come over, or whether it's a neighbor's or friend or whatever, he would say to his brother, "Who's that?" And his brother would say something, "Well, can't you tell? Like, that's Orange, that's Uncle Dave." Okay. And he really thought his brother was making this up his entire life, and he just thought it was this big scam on his parents. And so he was kind of relieved to find out that it really was true. And then he went back and had a really robust conversation with his brother. All right, so the next thing involves magnetoreception, which is sometimes called magnetoception. And it involves all kinds of animals. So in the bacteria in the bottom left corner, that little row of orange things, those are what are called magnetosomes. And so it's magnetic material, which is all lined up in this bacteria, which is quite interesting because it helps animals. What these things do is animals have different mechanisms, and this bacteria has these magnetosomes, which allow them to read the Earth's magnetic fields. Like for instance, I know we all live in LA, but if you ever go into the country, like say Central California or Oklahoma or Texas, where there's big fields and the cows aren't being kept in a little pen, what you will realize is the cows almost always are all lined up facing the same general way. And in fact, that's usually in a north-south direction, which is kind of a cool thing. If you know it and you get lost, then you kind of know where north and south are. Some sea creatures have organisms. I wrote down which ones do. Sharks and stingrays, because I can never remember. They have something called an ampulla of Lorenzi, which helps them figure out where they are in the oceans. And then our avian friends. Our avian friends have two really cool systems that go on. First, in their beaks, they have something that is like a rare earth metal, a magnetite, which basically gives magnetoreception. Now, in addition to that, they have a chemical in their retina, which we don't have, okay? And what this does is that magnetic fields act on this chemical, and so not only can their beaks sense the magnetic fields, but their eyeballs then can actually see the magnetic fields. And so this totally explains how homing pigeons know where to go, and how birds, when they're doing their 1,000-mile migrations, know how to go back into time. All right, So hopefully you found some of this fascinating. And with that, we're done with the different types of sensation. And so the last topic is to talk about referred pain, which is also really cool to talk about too. So in order to understand referred pain, what you have to get first is that our visceral sensory neurons and our somatic sensory neurons use the same tracks in the spinal cord. So they'll use those same tracks in the anterior, posterior, and lateral columns to get up to the brain. Okay, so they'll travel right next to each other. Then they go to the somatosensory cortex. And the problem is because they travel together, now they're right next to each other. And the brain is not able to accurately figure out, is this coming from that or is it coming from this? Okay. And because of that, those nerve signals from some of those viscera are falsely perceived as coming from the somatic sensory neurons. So the organ sensation is falsely perceived as coming from either the skin or skeletal muscle. So there are a couple really cool ones which are very useful for clinical diagnosis. And the first one is the heart. And so here's the picture of how this works. If we look at the heart has autonomic nervous system stimulation. It has sympathetic and parasympathetic fibers. And the sympathetic fibers will travel up to the brain through the spinal cord, entering from T1 through T5. Now, also the skin dermatomes from T1 through T5 travel at the same time. And so the pain can be returned back to the skin dermatome T1 through T5, which is going to be in the general shoulder and inner arm area. So when people are having myocardial infarctions, heart attacks, lack of oxygen going to their heart, it is very common for them to complain about left shoulder pain or pain here, and they often think it's some kind of arthritis or they hurt themselves out gardening or something like that. The second example, and one that's near and dear to my heart, has to do with the appendix and appendicitis. So in case you don't know, your appendix is in the right lower quadrant of your abdomen, quite low. Okay, quite low, just a little bit, about a third of the way up between your inguinal ligament and your belly button. So it's much closer to your inguinal ligament than your belly button. Okay. And what happens is when you have appendicitis, the visceral sensory receptors will go and they will get crossed with the somatoreceptors that are going to the T10 dermatome, which comes across your flank to your belly button area. So people with appendicitis will often present with periumbilical pain or pain around their belly button. Like when we ask them to point to one area, they point to your belly button. And in fact, the pain will not move down to the right lower quadrant area for a lot of people because we'll operate before them. By the time the pain has moved down to the right lower quadrant, then significant damage has usually happened because the appendix is usually nowhere close to the inside surface of the abdominal wall. In order to move to the right lower quadrant, that means you have to activate fibers, somatosensory fibers down there in the right lower quadrant, which means you're irritating the peritoneum and like where the transverse abdominis muscle is. So oftentimes that entails the appendix having to have already ruptured. And the third great example we see all the time has to do with kidney and ureter pain, like for instance, somebody who has a kidney stone. And even though these are both posterior structures, your kidneys are sitting way back by your 10th, 11th, and 12th ribs, just anterior to those ribs, the pain is referred anteriorly to the groin area. Okay, so I hope that explained what referred pain was for you. And with that, we are done with the general senses, and we will come back and start our exploration of the special senses next. Thank you for all your hard work, and I'll see you shortly.